So our next talk is an invited talk from Yong Kiam. Yong Kiam is here in Singapore and has managed to find time to come in to give the talk in his very busy day. So I'm very happy to welcome him up onto the stage to tell us about CakeML. I wanted to mention actually, so CakeML, I think last time it appeared at the ML workshop was maybe a decade ago or more. So very happy to have Yong Kiam give us an update on all the things that the CakeML community has been working on over the past 10 years or so. So take it away.
So yeah, thanks for the introduction. So I'm actually not that busy today, but yeah. So anyways, so yeah, in the email that Sam sent to me when he was inviting me, basically he said there hasn't been much CakeML at the workshop. And yeah, indeed, I went back and looked at the proceedings, and the last time it appeared was in 2014, more than 10 years ago, at this workshop, and that was where actually the first CakeML paper appeared at Popple. And specifically, this was the abstract, and at that time, basically, we promised to discuss some plans for new optimizations, new compiler primitives, a new library, and some verified applications. And that's very nice because that's basically what I'm going to talk about today. In the first part of the talk, I'm going to talk about some of the major things that has happened in the CakeML ecosystem over the last 10 years or so. And then the second part, I'll talk about some applications which I have been working on over the last few years. Okay? So before going to that, I just wanted to show this picture, which is the number of lines of proofs and code that's in the CakeML code base, how it's evolved over the last 10 years. Basically, what I'm going to cover is this stuff. So right now, we're at about 750,000 lines of code. But if you include all the auxiliary repositories involved in the CakeML project, we're actually just over 1 million lines of code. So it's a pretty big verified. Thank you. It's a pretty big. Sorry. Hello. Okay. So it's a pretty big verification project by, I guess, most standards. Is it? Okay. Okay. So and what I wanted to say is that the project has been developed collaboratively by many people over the years. So I'm only going to be able to cover the stuff that I'm a little bit more familiar with, and some of the things I'm going to mention are more of the stuff that I've worked on more recently. Okay, so there's also a technical project overview paper, which was in ITP a few years ago, if you're interested in that. Okay, so going into the talk proper, this is sort of the plan. I'll start with an overview of what CakeML is, and then I'll do a deeper dive into some of the parts, and then I'll talk about its applications in trustworthy automated reasoning. Okay, so yeah, so what was CakeML in 2014, right, when it first appeared? So it appeared at Popple, and it received just last year the most influential Popple Paper Award. So the main contribution of this paper was to build the first formally verified compiler for a functional programming language, which we called CakeML, and it compiled from this source language down to x64 via bytecode language. Okay. Now, the verification at the time covered basically the entire compilation process, starting from type inference, parsing and type inference. Both of them proved sound. And more importantly, semantic preservation from the source language all the way down to the machine code model. Okay? And this had to include, for example, a verified big num library, verified garbage collection, and a verified runtime. Okay. One of the very interesting features of the CakeML compiler is it supports something called verified bootstrapping. So it's able to bootstrap itself and generate a correctness theorem about this bootstrap. And I'll tell you more about this in a few slides. Okay? Sorry. And all of this is built using the Hall 4 theorem prover. And what I'll talk about is basically what has happened since this 2014 paper. Okay? So, I think really the next step after the Popple workshop, the ML workshop that we attended at Popple, was to redesign and build a new backend for the compiler. Okay, and this was where actually I started getting involved in the project as an undergrad. Okay, so this picture, I'll zoom in a bit later. It's actually a view of the compiler as it is today. Okay, we go through 8 intermediate languages, basically sort of a block of front-end languages which are responsible for compiling away some of the more functional features, a block of intermediate languages which are responsible for turning a functional intermediate language into an imperative intermediate language, And then we have a bunch of languages at the end which are responsible for target-specific optimizations and code generation. Okay? The CakeML compiler today is not just targeting x64, it targets actually 5 different compilation targets. And it supports, for example, a foreign function interface, which in the context of our tools allows us to model interaction with the external world as well. Okay? And it's still capable of having compiler bootstrapping. As you can see, the compiler is pretty big, so we're able to actually bootstrap the entire, all of these passes. Okay, so zooming in a little bit, right? Starting from the top of the compiler, we have 2 intermediate languages which are responsible for functional level optimizations and compiling away some of the features. Okay, and then we have the block of intermediate languages, the intermediate layer languages. And I think the most important one here is probably this one in the middle here. It's a small block here, but actually it represents one of the most complex passes and with correspondingly complex proofs, where essentially we turn abstractly modeled data values into concrete machine words and implement them into the heap. Okay, so moving out of this language is actually where I am the most familiar with. We have an intermediate language which is responsible for low-level compiler optimizations, including, for example, register allocation for target-specific. Register allocation for specific targets. Okay. Now, once we exit out of word-lang, that's where we really start to go down into machine bytes. We have, for example, implementation of the CakeML stack. So CakeML manages its own stack, okay, and it also implements its own GC, both verified. Okay, and then we have compilation out of that into a flattened language, right, where we remove all the structured control flow. And finally, one of the things that may be a little bit surprising is that CakeML actually compiles and assembles itself down to bytes. Okay, so the correctness theorem actually applies to at the level of machine bytes. Okay, so I'll talk a little bit more about the targets and actually this CPU later. But you can see here we have both 32-bit and 64-bit targets, and each of these have some form of semantics modeled in the theorem prover itself. Okay. So this gives us a verified compiler, right? Which, you know, in the notation here, basically compiles some kind of source CakeML source program into a target program, and if you successfully do this compilation, what we have shown is that, of course, the semantics is preserved from the source to the target. So this is a little bit simplified, but I'll just go with this for now. Okay. But the CakeML project as a whole today is able to also offer guarantees about the source semantics, right? So I think since 2014, we have always had a type system or a type inferencer. And of course, the thing that we have formally proved is that, you know, if your program is well typed, then it cannot go wrong. In addition, we have also shown that the type inference is sound and complete with respect to the type system. But beyond that, you know, beyond just type soundness, we also offer tools that allow us to obtain functional correctness guarantees. So we have these tools called the translator, and what these tools are capable of doing is taking as input a Hall function, so a function in the logic of a theorem prover, and automatically generating CakeML programs. So the base translator actually generates pure programs, and it provably implements the Hall function. And the monadic version of this translator actually generates stateful CakeML programs via reflection of the monad. Okay, and this requires you to write a higher order logic function within a certain monad. Okay. So as you can see, this is sort of like adding a little bit more state. And if you really want to go for sort of a full stateful program using arrays, exceptions, and whatnot, then we actually also have a formal framework for doing separation logic style reasoning based on characteristic formulas. And this is verified to be sound against CakeML semantics. Okay? What's important is that actually all of these tools are verified give us verification guarantees about the source semantics, but the guarantees actually compose with the compiler correctness theorem. So we can actually obtain functional correctness guarantees about the generated machine code at the end. Okay? And that's actually what allows us to obtain what we call a verified obtain a verified bootstrapped compiler, right? So I just wanted to show this a little bit of intuition for this. Right, so the CakeML compiler itself is actually defined as a bunch of logical functions in a theorem prover called Hall. Okay, it looks a little bit like this, I mean, simplified. Okay, and we proved the theorem that I showed just now, which is semantic preservation from the source to the target. Okay, now what's interesting is we have the translation mechanism, and what we can do is we can take the translation mechanism and apply it to the compilation function itself. Okay, and this is going to generate us a CakeML program, right, whose semantics is equal to the compilation function. Okay, this is through the translation. Okay, and now one of the things that you can do in many provers today, including Hall 4, is you can take this compilation function and apply it to the AST of itself generated by the compiler, sorry, by the translator, and you can sort of run this inside the theorem prover and obtain a theorem that says the compile of this piece of AST is equals to some machine bytes, okay? And this is basically the byte level implementation of the compiler, okay? And now if you put these three theorems together, what you get effectively is that the semantics of the machine bytes actually implements the compiler itself, okay? Which, yeah, if you look at these chains together. So this sequence of bytes is what we call the verified bootstrap compiler binary, okay? So maybe I'll give you a few seconds to look through the sequence of things. Yeah.
Are all these pieces put together in a Hall, or?
Yes. Yeah. So all of these are proved as theorems in Hall, and this thing is also proved as a theorem in Hall.
Yeah, but they're put together. Okay.
Yeah, it's all in Hall, and we have this theorem in Hall. Yeah. Yeah. Thanks for the question. Okay. So yeah. So of course, in reality, the bootstrap is not as sort of clean as what I showed on the previous slide. So most of the equalities I showed on the previous slides are actually some kind of relations. And well, as we expanded the compiler to this whole thing, we actually needed to also expand the kind of things, we expanded the compiler, also needed to expand the kind of things that a source language has so that we can actually bootstrap the compiler. But the good thing is actually we are able to bootstrap it, which means that our source language is sufficiently expressive to, for example, support the word level manipulations that you need to do assembly. Okay. Some other details, for example, carrying out the translation, you need to be a little bit more careful. For example, for some of the compilation parsers, you really want to, for example, make sure you use some stateful features so that it actually runs okay in speed, right? It doesn't take forever to compile. And the full bootstrap is actually very expensive. We actually have nowadays regression infrastructure that runs for overnight, maybe about a day to actually finish the whole bootstrap. Okay, it used to be more than a day. It used to be like 2 or 3 days, but nowadays it's a day. Okay, so that's the compiler bootstrap. But if we take a step back, the bootstrapping is really in an instance of what we call binary code extraction. And what that means is we are able, inside a theorem prover, to verify software all the way down to their machine code implementation. And this is verified against the machine code semantics. Okay, and this actually, from the perspective of an ITP, eliminates part of the trusted base. So for example, we don't need to trust code export from an ITP. We don't need to trust, of course, an unverified external compiler. Okay, so I'll talk a little bit about binary code verified applications in the later part of the talk. Okay, so that's a quick overview. And now I want to sort of dive a little bit deeper into some of the parts. I think I've chosen to start from the top and go down. So, okay, so in terms of verification tools, I already mentioned the translator and the characteristic formula. So what does the process look like? So to use the CakeML translator and monadic translator, what we do is write a Hall function, so a higher order logic function. And this is also known as a shallow embedding. We write it in a theorem prover. We prove some properties about this function, okay, and then we call the translation mechanism to automatically generate a pure, or in some cases, a stateful CakeML function, and it automatically shows that this CakeML function's semantics implements the given Hall function, okay? So we also have, as I said, if you want to go beyond what the translator and monadic translator are able to give. We also have something called characteristic formulas, and this is a framework that essentially allows us to do separation logic style reasoning over CakeML programs. And what that means is we can write so-called deeply embedded CakeML inside the theorem prover, and then again state and proof properties, but this time about the deep embedding. And what that means is we need to use sort of customized tactics to reason about CF specifications, so characteristic formula specifications. So one of the things with CakeML's CF framework, for example, is it supports essentially all of the imperative features that you can find inside CakeML, state exceptions, talking about the FFI, and it even supports reasoning about diverging programs, so reasoning about infinite traces that are generated by divergent programs. Okay, so I just wanted to mention, well, one of the things that's a little bit of a drawback right now is that the automation we have isn't that great. It'd be nice to have a better library for this. Okay, what's important actually is that these two things are compatible. What that means is in a typical verified application for CakeML, what we would do is kind of start by writing everything purely, right? And then using the translator to automatically generate CakeML. And then as we sort of profile and go along the way, we find that, well, maybe some of the functions really should use some form of actual state. And then we would actually swap out that function for a CF verified function, okay? And this is maybe a little bit of unfamiliar workflow, but what it allows us to do is really sort of use this part selectively to optimize whatever application we're trying to build in a verified way, okay? So I have some of these boxes here, which are some of the wish lists that I have. As I mentioned, it would be nice to have a more streamlined program verification framework for CakeML, including, for example, speeding up and automating our separation logic libraries. Okay. So going a little bit down into the language front ends, so besides CakeML, what we have done is also built on the compiler backend as a backend for other languages, right? So one of the first projects I think was this choreographic language. So it's a language for describing distributed computations, right? And what has been done is, again, verified compilation into sort of a group of CakeML processes communicating via the FFI. This is also, this compilation down into the instances is verified as well. Right, another project was to provide a Haskell-like front end for CakeML, including supporting lazy call by need semantics, okay, with monadic reflection. So you can see this is a picture I took from the paper. It basically starts from a Haskell-like front end and actually compiles into CakeML source. That's a project. So that's another project called Pancake coming out from the folks in Australia. This was a system-oriented programming language, and it actually targets some of the lower-level languages in CakeML. What it does is actually compiles into the middle end of the back end of the CakeML, the lower end of the CakeML compiler, which is then responsible for doing things like register allocation and target-specific optimizations. Okay, so there are a few other front ends. Most recently, we built one for Daphne, including a verified compiler and verified VCG. And there's going to be, there's also a front end for Scheme with support for first-class continuations, and there's going to be a talk by Pascal, I think, later today. Okay, so I think what's interesting about building these new language front ends is, of course, the compiler verification question, but also, there's also the problem of can we build associated optimizations in the compiler backend in order to speed up some of these applications, and at the same time also, of course, speed up other applications as well. Okay. So going all the way down to the end of the compiler. So as I said, we have both 32-bit and 64-bit ISA targets. Okay, all of them are implemented essentially by first compiling to a generic assembly language and then encoding this assembly language into the respective backends. Okay, all of these, well, we have essentially verified assembly for all of these targets. But beyond that, some interesting things that has happened over the last few years. One of them is our ARM ARM8 target. So we call our ARM8 target semantics actually authoritative because it's verified against ARM's officially released ISA model. So we have a compilation theorem that says the CakeML compiler actually correctly preserves semantics down to this particular model. Okay. We also have this silver ISA over here, which was a project on building a proof of concept piece of hardware, right, which is verified down to its Verilog semantics. And also we have a compilation theorem that goes down all the way to verified Verilog. Okay. So in future work, some of my students and others are working on, for example, broadening the class of targets that we have, in particular WebAssembly. So verified compilation, I think, from slightly above here down into WebAssembly. And one of the things that I think would be interesting is to revisit this design decision to have generic assembly layer over here, because that really blocks us from using some of the more specific instructions that might be available on some ISAs. So we do want to kind of revisit this and see if we could maybe tweak this a little bit and to support more instructions, let's say on x64. I'm sorry, to use more instructions on x64. Okay, so one more thing that I haven't mentioned so far is that actually the compiler that I've shown so far is really, you could consider it the third iteration of the compiler, because the thing that we have added most recently is what we are calling dynamic evaluation or computation. And what that means is, in the source of CakeML as it is today, we have an operator called eval. Right? And what it does is, at runtime, if you give this eval a value which happens to decode into CakeML abstract syntax, right, it will actually run the bootstrap compiler on this piece of syntax, and then it will write the compiled bytes in your memory, in your instruction memory. You'll write those bytes into there, and then it will jump to those installed bytes and actually execute it. So in other words, we can actually install new code at runtime, right? And this allows us to, I guess, rebuild a verified read eval print loop. And more importantly, actually, this actually fulfilled one of the really early goals of the CakeML project, which was to build a verified interactive theorem prover, which we call Candle, which is built on top of CakeML. Okay, so I just have a quick demo of this. So actually, oh, I didn't realize it's going to be too small. Let's see. Make it, let's see. Okay. So by default, CakeML, well, so this is compiling the compiler itself, and then by default, CakeML is actually able to compile programs that look like this. So this is just the factorial program, which I actually asked ChatGPT to generate. But I mean, I could have written it myself, but anyway. So you can see actually on this line, this is the CakeML bootstrap compiler called on the factorial program, and it generates assembled bytes. And yeah, it actually runs and generates the factorial. But actually what you can also do is, let me see if I prepared so what you can also do is actually run CakeML in REPL mode, right? And in this mode, you can actually interact with it. So I'm hoping you can see this. Yeah, so you can actually interact with it. And this, what's happening behind the scenes is actually, as I said, taking the code, parsing it, turning it into CakeML abstract syntax, running the bootstrap compiler on it, taking the bytes, putting in the memory, and then jumping to those bytes and running it, right? So that's what's happening here. And in fact, what you can do is, let's see, copy this, and then you can do that, or like that, or yeah. So that's what we can do with the REPL. Okay. So as I've written here, one of the drawbacks that we have right now is that because we have to do this thing where we write into instruction memory, we're limited to systems that don't have write XOR execute at the moment. So that basically rules out all Mac OSs. But we're working to lift this limit as well. Okay. So for the rest of my talk, I'll be talking a little bit more about an application that I've been working on using CakeML for the last few years. And this is in what's called, I guess, trustworthy automated reasoning. Okay, so what does that mean, right? So here's the question. If you have an automated reasoning tool, right, you give it some verification problem. Let's say it's a set solver and you give it a CNF. If it's a SMT solver, you give it something, a problem in SMT-lit, and so on, right? And you expect this automated reasoning tool, in most cases, to give you some kind of result, right? Whether your problem is unsatisfiable, whether there's a model, and maybe it prints a model out, okay? But the question is, how do we trust the correctness of this result, right? So for satisfiable cases, typically you get a solution as well. And in that case, it's pretty easy to check the answer. Just make sure it satisfies all of your constraints. But in other cases, we are interested also in, for example, unset results, right? Which would correspond to, for example, your circuit doesn't have any counterexamples, your program doesn't have any, your specification doesn't have any counterexamples. And in those cases, what we're interested in is for the automated reasoning tool to be able to justify its answer beyond just saying that, well, there are no counterexamples. Right? So in the automated reasoning community, this is a topic that has got a lot of attention in the last few years to ensure that their tools are actually sound. And so the approach that's been taken up by the community is something called certifying algorithms. Okay, and what this is about is essentially many automated reasoning tools today are able to generate something called a proof or a proof certificate. And this is a proof of, for example, unsatisfiability, which you can then feed together with the original verification problem into something called a proof checker, which is able to check the correctness of this certificate in an independent way. Okay, so this is the sort of general setup, okay? And as you can see in this picture over here, as you can see in this picture over here, really what this does is it reduces the trusted base from having to trust this complex automated reasoning solver to just the code base of this proof checker, okay? And what's perhaps more interesting for verification is that this proof checker itself, it can be formally verified. Oh. Hello? Am I supposed to use this? Oh, okay. Okay, so this proof checker itself, it can be formally verified. Okay, in particular, it can be formally verified using CakeML. Okay, and that's what I'm going to talk about. And so what I'll do is I'll tell you about what we have been doing in the set scenario. So we have a set solver over here. And as I said, a set solver is able to either produce a satisfiable result or an unset result. Okay, and in the satisfiable case, you get a satisfying assignment. All you need to do is to plug it into your formula and check that it evaluates the true. But in the case where you get an unset answer, most modern set solvers today are able to generate something called an unset proof, which you can feed into an unset proof checker. Okay, and it looks a little bit like this, right? So if you give a set solver a problem, this is the standard input format in conjunctive Boolean formula in conjunctive normal form. Okay, what the set solver will print out is a sort of a sequence of numbers that look like this, and this is the file that kind of goes into your proof checker, where you can tell whether it's, and then the proof checker is responsible for saying whether it's valid or not. Okay. Now this started being used in the set community about 2014. Okay, and one of the questions immediately got was, how can we further enhance the trust in this proof checker? Okay, and I think the verification community really stepped in at that time. So around 2017, people figured out that, well, if you just made the solver print out a little bit more information, you can actually have a formally verified proof checker. And at the time in 2017, there were a bunch of different proof checkers which were able to check such proofs. Okay, so we can skip these details, but so just to give a little bit of a summary and a timeline, every year the world's best set solvers compete at this international set competition. Okay, so since 2014, proofs have been mandatory for all set solvers participating in the competition. Okay. Now, since 2017, not just proofs, but you also want the proofs to be checked by a verified proof checker. And 2021 was where CakeML started coming in. So in 2021, the formally verified proof checker that was used in the set competition was built using CakeML. Okay. Since 2023, actually, a set competition decided to say we're going to allow you to use any proof format that you want as long as you can provide us with a verified proof checker. So we actually provided an alternative format as well. Another thing also happened in 2023, which is that one of the best open source set solvers out there, called CakeML, it started to be able to stream these proofs, right? And in particular, it could stream the proofs directly into the CakeML-based proof checker. And what that means today for set solving is that verified proof checking, which helps to improve trust in set solvers, can be done for free, like actually free. So the proofs can actually be output and checked with negligible cost to set solvers. So I wanted to show this in action. So yeah, so what I'm running here is actually the set solver that I mentioned. And what it's doing is I've passed it a CNF, which is a input problem. And what it's doing is going off and solving that CNF. All right. Eventually, it will show unset, but this takes about 2 minutes. Okay. But what's happening here is that actually, if you can see in my top over here, right, CakeML is running. This is a set solver. And running next to it is actually the proof checker. And what's happening is that this thing is writing straight to a pipe that goes into the proof checker. So the proof checking is happening directly at runtime for the solver. And of course, there's a verified soundness theorem for CakeML if I didn't mention that. So anyway, this will take a few more seconds. I'll come back to it. But that's what's happening. And yeah, well, actually. So I think every talk nowadays has to have a slide about AI. So this is my slide about AI. So something very interesting happened in the 2025 set competition, actually. So it was won by this set solver, AE Keyset MAB. And well, you don't really know what these means, but AE was their framework for using LLMs to tune the implementation and heuristics of set solver. So this was won by an AI-tuned set solver this year. And actually, it won by a significant margin over the second place solver this year, right? So I think what's interesting is that these results were actually cross-checked by verified proof checkers. Another recent paper, which I think is not yet refereed, claimed to even surpass this solver in performance, right? So, and here they actually used AI-based agents to autonomously evolve entire set solver repository, not just tuning heuristics. So in the paper, they actually mentioned that proof checking was used to make sure that the generated solvers were actually doing the right thing, right? So for me, I mean, as I said, this is not a refereed result. I'm not saying that it's definitely correct, but I think it'd be really interesting to see what happens at the next year's set competition, if anyone's interested in that, okay? But what I wanted to say is that this approach of certifying algorithms and building efficient verified proof checkers seems to be a nice way for us to make sure, at least in these domains, that AI-generated software behaves as intended. Okay, so, right, so going back to the solving, so what you can see is that the solver finish up. I think it decided that the problem is actually unset. And at the same time, the CakeML verified proof checker also said it's unset. And well, I mean, you can't see it right now, but actually this probably happened just a split second after this thing finished. Okay, so proof checking is really for free in the set domain nowadays. Okay, so of course we have gone way beyond set today. We actually have a range of formally verified proof checkers in CakeML. For example, for set solvers and their extensions, we have proof checkers for approximate and exact model counting, for 0-1 ILP, for various other combinatorial solvers. We have one for MIP. Yeah, I mean, if anyone's interested, we would be happy to build more verified checkers for new automated reasoning tools. Okay, and all of these tools that are shown over here, they have been verified sound to the machine code implementation using the binary code extraction mechanism that I've talked about earlier, including both to x64 and to the authoritative ARM8 semantics. Okay, so I think this has been a very fruitful collaboration between some of us in the CakeML community with the automated reasoning community. Okay, so what's there? So one of the points I wanted to make with my talk title as well was the back again part. So I think this process of building new verified proof checkers in together with the automated reasoning community has really given us also insights into how we can improve the performance of CakeML generated applications and also tooling. So for example, one of the things that I already mentioned earlier is, can we streamline our verification tooling? And can we improve the prototyping, benchmarking, or profiling techniques that we have for CakeML applications? Along the way of building these proof checkers, we have, of course, developed new libraries, which allow us to, for example, do streaming I/O support, hash tables for some of these proof checking algorithms. One of the things that, at least, I don't know if you think this is nice or not, but one of the things that we can do, because we are in full control of the compiler, we can introduce new primitives that we want, that we need for the proof checkers, and we can actually efficiently support verified compilation for these primitives all the way down to machine code. One of the big things that we are hoping to build soon is a verified big num arithmetic library. Sorry, we already have one, but we want to improve it so that we can better support mixed integer programming proof checking. Okay, and of course, I mean, many of these involve verifying new compiler optimizations, low-level code generation optimizations, and of course, we are always interested in expanding CakeML verified proof checking to other domains as well. Okay, so just to summarize, I would say the CakeML ecosystem has grown very substantially over the last 10 years since we appeared at the workshop, but there remains many more questions to be tackled. And at least for what I'm working on, I think CakeML has had a really nice symbiotic relationship with automated reasoning, and I think we are going to continue that for the next few years. Okay, so just wanted to say we're always looking for new contributors, so please feel free to approach me if you're interested. Thank you.
So time for questions. If you want to ask a question to Yong Kiam, just come on up.
Sorry, Shagari. I've been wondering because I have the impression that all you presented has been created anew for CakeML, and I understand why you need to do that because you want to prove everything, so you have to build it and prove it simultaneously. But were there also attempts, since you're using ML, to well, compile some software with CakeML and even maybe try to prove something about it? Some existing software? Well, I suppose Isabelle would be too big, but...
Right. So in terms of existing software, we have tried to, I mean, one of the things that we're maybe a bit lacking is in terms of benchmarking. We have tried to actually benchmark the CakeML compiler on existing benchmark. But in terms of verifying existing code, I don't think we have tried that at all, actually. Most of our code is basically written from scratch and for verification. Thank you.
Hi, I'm Cesar from MPI. So I think my question is related to the previous question.
Right.
So did you try, I don't know, to compile some of the libraries of OCaml, and like how much does it support, how expressive is CakeML to compile existing OCaml code? Right.
So what we do have, I don't think we have tried like OCaml code, but what we have tried is actually, so what I mentioned just now is that we not only have a verified REPL, we actually have a verified implementation of an interactive theorem prover called Candle. And Candle is actually, the way we supported it was we made a front end that resembles OCaml. So Candle is actually a clone of Howlite, if you know that theorem prover. So Howlite is a theorem prover which is actually written in OCaml. a slight variant of a camel syntax, but actually it's, this tool was able to handle quite a large fragment of the whole-like libraries as is, almost as is.
Okay.
Yeah.
But my impression was that the idea to have a verified compiler for ML is to kind of not necessarily. I mean, it's twofold, right? I mean, on one side you can verify code in a proof assistant, but then you can also just compile the code and have the guarantee that the compilation is verified,
Yes.
right? So one can compile code without necessarily verifying the code. So you're saying that CakeML doesn't really is not able to necessarily compile OCaml and.
Well, it wouldn't be able to. Right now, I don't think it would be able to support the full range of language features that we have in OCaml. So I would say the language features that we have right now are, we are sort of adding them as we build things. So I mean, what we have is enough to support the applications that we have built. Yeah.
Thank you.
One of the aspects of CakeML that I've always been fascinated by is the proofs, in some sense, of efficiency. I mean, it's not really efficiency, maybe, but like a bound, right? Maybe I need to be able to prove that within a certain space bound, the executable will actually complete and succeed in its execution. And I'm just kind of curious, is there more to do there, or are the existing results you have completely sufficient for all of the work that's been done in CakeML? I don't know, maybe you can just say a bit about that aspect of the project.
Yeah, so I think it's like slightly hidden here. So we do have a cost semantics for CakeML as well, okay? But we don't actually prove the cost bounds for most of our applications. What we have actually in the compiler correctness theorem, which I showed as a lie over here, is that actually the source semantics, the target semantics will behave exactly like the source, except if it runs out of memory. It will actually simulate a prefix of the source only. Because of course the source semantics has unbounded with integers and the target semantics has finite memory. We are going down to a very concrete machine model, right? So we don't have infinite memory. So the answer to your question is that, yeah, we have a cost semantics which we have used for some examples, but I would say, I mean, if one were to seriously look at this, I think we would, for example, want to have more automation for proving the cost bounds for new programs. Right? So another thing to mention is that actually in the applications that I have in trustworthy automated reasoning, sort of what you want at the end of the day is a guarantee that if you print unset, then the problem was actually unset. And so we haven't really needed these bounds because, I mean, if it runs out of memory, it runs out of memory. So you don't get unset guarantee, but in terms of soundness, it's still sound. So yeah.
Thank you.
Thank you.